Okay, so what if a computer could play by a completely different set of rules? A world where a single particle can be in two places at the exact same time. Well, that's not science fiction anymore. It's the wild idea at the heart of quantum computing. And listen, this isn't just about making our computers faster. We're talking about building a machine that thinks in a fundamentally new way. A way that could, honestly, change just about everything.
And that potential? It's huge. Just think about it for a second. What if we had a tool so powerful it could solve problems that right now are basically impossible for even the world's best supercomputers? I'm talking about designing brand new life-saving drugs, molecule by molecule, or discovering new materials that could completely revolutionize how we use energy. This is the incredible promise of quantum.
So here's our game plan for today. First, we're going to go beyond simple bits and bytes. Then, we'll dive into the new quantum race that's heating up. We'll look at the impossible problems this tech could solve, face the really big hurdles ahead, and then finally, we'll look at what our quantum future might actually look like.
To really get what's going on here, we have to understand the rules. And in the quantum world, well, the rules are just plain strange. We're going way, way beyond the simple ones and zeros that power the computer or phone you're watching this on. It all starts with this fundamental difference. Your phone, your laptop, they all use bits. You can think of them like a simple light switch. They're either on or they're off, a 1 or 0. But quantum computers, they use qubits. And this is where your brain's got to do a little backflip. A qubit can be a 0, a 1, or both at the exact same time.
Yeah, both at the same time. This wild property is called superposition. The best way to picture it is to think of a spinning coin. While it's up there in the air, it's not heads and it's not tails. It's kind of both possibilities at once. It's only when it lands or when we measure it that it picks a side. Qubits live in that spinning state of pure potential.
And believe it or not, it gets even weirder with something called entanglement. This is where two qubits become linked. I mean, deeply linked. So if you measure one and it turns out to be a 0, you instantly know the other one is a 1, and vice versa. And here's the kicker. This connection is instantaneous, even if they're on opposite sides of the universe. It's so weird that Einstein himself called it spooky action at a distance.
And look, these aren't just strange theories anymore. As IBM points out here, we're finally figuring out how to control these spooky phenomena. Superposition and entanglement are no longer just weird quirks of the universe. They're becoming powerful new ingredients for computing. They let a computer explore millions of possibilities all at once. And that, right there, is the secret sauce to their power. So being able to harness these strange rules has kicked off this fierce global competition. I mean, this is not some quiet project in a university basement anymore. It's a full-blown race to build the future of computing. Right now, we're living in what experts are calling the NISQ era. That's NISQ, which stands for Noisy Intermediate Scale Quantum. Basically, it means that the quantum computers we have today are really cool and really powerful, but they're still kind of small, and they're super sensitive to errors or noise from the outside world. Think of them like the very first room-sized computers from the 1940s. A ton of potential, but still in their infancy. And the race to get beyond this early era is intense. You've got the huge tech giants like IBM, Google, and Microsoft pouring billions of dollars into this. But you also have these super clever, nimble startups like Oxford Ionics and Riverlane, and each of them is trying a totally unique approach to building a stable, powerful quantum machine.
You can just feel the excitement in this field. As Dr. Chris Ballance from Oxford Ionics puts it, we're getting close to a ChatGPT moment for quantum. A moment where years of slow, steady progress could suddenly just explode into a massive, world-changing leap forward.
Okay, so with all this money and all this excitement, what are we actually going to do with these incredible machines? Let's talk about the real-world impact and the kinds of impossible problems they could finally help us solve.
The potential impact here is just staggering. It touches pretty much every major industry. I mean, imagine designing new medicines by simulating molecules perfectly, or creating financial models that can actually predict the market with stunning accuracy. This tech could supercharge AI, make modern encryption totally obsolete overnight, and solve logistical problems so complicated that we can't even touch them today. But hold on, don't expect to trade in your laptop for a quantum one anytime soon. As Marcus Doherty from Quantum Brilliance points out, the future is all about hybrid solutions. Our regular computers will still run the show, but they'll call on these quantum processors for the really specific, brutally difficult calculations that only they can handle.
Of course, if this were easy, we'd already be living in that quantum future. The reality is, there are these enormous technical hurdles we still have to clear. And these challenges are exactly why building a useful quantum computer is one of the greatest scientific quests of our generation.
So, what's the biggest problem? Well, qubits are incredibly fragile. I mean, the slightest vibration, a tiny change in temperature, and poof, your entire calculation is ruined. It's a process called decoherence, so we need to constantly correct for these errors. On top of that, we have to figure out how to scale up and build millions of stable qubits, write completely new kinds of software for them, and, oh yeah, train a whole new generation of engineers and scientists who can actually build all this stuff. But the good news is the industry has a laser focus. According to Steve Brierley of Riverlane, we're now officially in the quantum error correction era. The entire global community is on the same page about this one mission. We have to make these fragile machines reliable enough to actually do useful work.
Okay, so with the challenges crystal clear and everyone focused on the same goal, we can actually start to see a credible path forward. We can see the roadmap to those stable, world-changing quantum computers we've been talking about. And this is basically that path. Think of it like building a skyscraper. First, you have to master the foundation, right? That's qubit stability. Then you build the core steel structure. That's robust error correction. Only then can you start building upwards, scaling up manufacturing, adding the complex systems inside, the new algorithms, and finally completing a truly fault-tolerant machine that won't just collapse.
And the vision goes way beyond just a single computer. We're talking about a future with a quantum internet that allows for totally unhackable communication, or quantum sensors so precise they could map what's deep underground or even see inside the human brain. In a future where quantum and classical computers work together, hand in hand, seamlessly.
And here's maybe the most important takeaway of all. Just like you don't need to know how a transistor works to use your smartphone, Dr. Valence reminds us that you won't need a PhD in quantum physics to use a quantum computer. All that mind-bending complexity is going to be under the hood, empowering all of us. Which brings us right back to where we started. This technology is coming, and it's going to give us a tool to solve problems that we once thought were impossible. So I'll leave you with this question. Once we finally have that power, what impossible problem do you think we should solve first?